Hello everyone, this is going to be a self-driving project using Python and OpenCV. We're using the simple 3D car simulator game, which is an online version. You can simply go ahead and have a free drive on this game. And we will use OpenCV to understand where the lanes are, and we'll give control to the car in terms of driving around the lanes. So let's get started. A few terminals, a few libraries that we need to download for this project would be pip install. Let me maximize this a little bit so you can see this. So on the bottom, I'm downloading all the files that we need. First is pyautogui, which is pyautogui. And this will allow us to take images or screenshots from our computer so we can use it. Normally, in a given scenario, you would use information coming out from a camera, but here, since we're using a game, we will just use screenshots. So pyautogui is one of the things that we need. Then you have OpenCV, Python. Then you will be also using some keyboard functions and some Windows terminals so that you can use your mouse and keyboard through Python. For that purpose, there are some libraries called as Win32 API, and this will allow us to control the Windows. Then you have keyboard. This allows us to control the keyboard, of course. I already have these installed, but in your case, you can have pip install, and all these libraries can be simple taken care. I did include the pyautogui initially, and you can have all of that in the same line and just simply install them. NumPy is also needed, but NumPy also comes through OpenCV, so we are covered over there. Now let's come back to the code. I'll minimize this back again so we can see the game itself. First thing we will do is, like we normally do in a camera-related project, we try to take the image from the camera. Here we'll try to take this image, which is the screenshot of our screen here. So let's import all the libraries. The first thing for this purpose, we need the pyautogui. So we say import pyautogui as py. Okay, so py is important, and now using py, we can just create a simple function that can take a screenshot. So we say, hey, def take screenshot. So whenever we call this function, it should simply return a screenshot of the image. And for that purpose, pyautogui has a function called screenshot, and it returns an image i.screenshot. And we need to specify where the screenshot has to be saved and what portion of the window do you need. Do you need the whole screen, or you just need a certain portion of your screen? And in our case, we don't need the whole thing. We just need the particular portion. So we need to give out the coordinates of this particular screen. So for that purpose, we first give out this location or this file name that we have to see. So we call it as screen.png. And this is the file name with which it'll be saved. The next is we want to specify the region of this coordinate. Now we don't know what these coordinates are, where these points are located, and for that purpose, pyautogui has another function giving the cursor position. So we open this Python console here in the bottom, and we'll have a simple code. We'll say import pyautogui as py, so we can run this here in the console directly, and we say py dot position. And this function will simply give us the position of where our mouse is located. So if I just run this, it'll give us the location where the x coordinate and the y coordinate are so and so. Now, for our purpose, we just need to know where the start point of the screenshot is, which is going to be, let's run this here. And I put my cursor here and I press enter. So I get x is equal to 5 and 109 is 1. Similarly, I'll go to this particular corner. We just need the bottom and the top left and the bottom right corner, and that can give us indication of what the width and what the height is. So you just do another position, and here in this case, we get x is equal to 935 and y is 636. Now, the next thing is to just specify what the region is going to be. The region, like we saw, it's going to be bounded by all these x and y coordinates. So I'll put 5, I'll put 109. I always get this order mistaken, so we'll test run this and see how the screen comes out to be. We have 935, and then finally we have 636. So let's save this and see how this works. IM, and it just simply creates screenshot. We'll call this function take screenshot from our main line. Let's run this and see how it works. And if you open the project file, we'll see there's a screen.png saved here. And we can see that it's saving the screenshot. It's also giving, let me maximize this so we can see the whole portion. If you're getting any unnecessary information, it looks like this 3D car simulator, this particular portion we don't need. So we can reduce the height a little bit. So we come back, and instead of putting down here, the code we have over here, let's minimize this back again. So instead of 636, we can try maybe 536 and see how this works. Coming back to the project, open this again. So it has reduced the screen. I think another 1 point should be good. This is just to avoid any unnecessary noise. Instead of 536, I might just put 534, and that should hopefully take care of it. So coming back to the project, we have the screen, and this is a simple screen that we can now work with. But let's start pre-processing this. Close this. Now, once we have this image, now OpenCV should be able to read this. We use pyautogui to take the screenshot, but this image comes out in a different format. And this format is not user-friendly for OpenCV. And for that, let's import OpenCV, import CV2, import numpy as np. And once we have all these functions, let's start converting this image into an OpenCV-friendly format. And for that purpose, we'll just we'll update the img equal to numpy dot array. So we'll convert that image, which pyautogui downloaded, as an array. So im the numpy array im. So now we have created this img image. This img image, if we were to simply display it, it'll be in a different format. So I'll show you cv2.im show. I will just create a simple window and we'll display this image. We also need to give out the wait key command. That way we are not, the IM show window stays there for us to see. Next, we have cv2 destroy all windows. Perfect. So once we display it and we close it, we get this function. So we have play. We can see this particular image is a little bit different to what the original image looks like. The main colors are different because normally images are read in an RGB format, red, green, blue, but OpenCV reads in a BGR format, which is blue, green, red. So it's the other way around. And for that purpose, we're getting this information incorrect. Now let's close this. And instead of numpy array, just numpy array, we will convert this into a BGR format. And for that purpose, we have this OpenCV function, which gives img equal to cv2 convert color. And convert color, we give out the original image, which is img, comma, cv2 color underscore rgb2 number 2 BGR. We have BGR here, and that takes care of our conversion from RGB to BGR. At this stage, if we were to use imShow function, so instead of showing it here, if we show it after this step, img should be hopefully of the original color that we saw. So let's play this once again, and you can now see that the window now has the same color as the original game screenshot. Perfect. So this is working. Now we have a function that can easily take screenshot, similar to taking images from a camera. So we normally don't want them to be shown as an imShow function, so we'll just remove that. Now this function takes screenshot, takes care of it. Whenever we need it, we can call it. Once we have this function created, we will now use something called as a Canny Etch detector to detect all these links. The way Canny edge detection works is it looks through the image and looks for any gradient changes. For example, the road is of a certain color, then you have a certain markation here because of this lane right here ending over here. There's a black color, shadow that comes up here. So that's a certain demarcation from the image. And you have the pave, which is a little bit different in color. Again, you have this white color that comes out again, which is also in a different color. Similarly, the yellow color of the car, all these shapes and different features. So it basically enhances all those features from an image. So we'll use something called as Uncanny edge detection to take out the edges from this image. So for that, there's a simple function. Now, once we have the screenshot, we'll just return the image that comes out of the screenshot. And now we'll create this Canny edge image. So Canny is a function, and it'll take this image, whatever image that we give, and it'll create an edge file. For Canny to work, we first need to convert it into a grayscale image. And for that, we also have that convert color function. So we say convert color, color, and instead of converting into BGR to gray, we'll BGR RGB to BGR, we'll convert it into BGR to gray. IMG-CV2 blur underscore BGR to gray. So this will create us the gray color or grayscale image. Now the Canny edge detection needs a filter. A filter gives out information about how big this edge should be, the minimum edge. And in our case, these edges, these lanes that we are interested in, this is the demand or the biggest feature in the image. So these lanes or these images are going to be, or these lanes are going to be the maximum size in this image. All the other demarcations that we see here, these edges, these are all smaller compared to the lane size. So we can give a kernel size. Let's say kernel or this window size is say maybe 5. We'll use this 5 to create the Canny. We'll create a blur effect on this in order to remove unnecessary noise or unnecessary edges that we are not interested in. For that purpose, there's a Gaussian blur function. And this Gaussian blur function works as gray bracket kernel. So this is creating a window of 5 by 5, and it goes through the whole image. And wherever the edges are greater than 5 by 5, it will create an edge for us. And we'll give a filter of 0, and that's about it. Once we have this blur or Gaussian blur done, we create this Canny. Canny is equal to CV2 Canny blur image on the blur. Now this is a window size of 50 by 150. This is again giving out the edge information about how big our edges should be. Next, you have return. And we'll try to see how this Canny image looks like. So we first call the screenshot, take screenshot. And once we have the screenshot, it gives out an image. And we'll call this image frame, maybe frame, like a frame from a camera. Frame is equal to take screenshot. And we'll send this frame to a Canny edge detection. And that will return a Canny image, which is equal to Canny. And the function will take the image frame. Once we have this, we'll just run a CV2 imShow command. We'll call a window by just the word win, and we'll just display this Canny image. Once we have this, we just simply display it, CV2 wait key 0. And once everything is done, we just destroy all windows. That takes care of the displaying of the Canny image. So let's run this and see what comes out. So it looks like it's creating a Canny image for us. And you can see the lanes that we are interested in. They are shown, and there are certain other lanes that are also being shown, which we are not interested in. What we can do is we can create a region of interest, and we can tell the code that we are only interested in the lanes that are starting from here to this region. So this triangle that we see here, that's the triangle that we are interested in, and we are not interested in the whole rest of the image. This is nothing but noise for us. So we need to just emphasize on these lanes, and we'll create a mask that will help us, differentiate this particular region from the rest of it. So we close this and we come back here. And once the Canny is created, we will now create a region of interest. And we'll call it as def region of interest. What's the spelling of interest? Okay, once we have image, all this is created. And now we will create a mask of the image and define how much it's going to be. Let's find out the image height and shape, which is given by image dot shape 0. The width of the image, which is given by img dot shape 1. So we have the width and the height of the image. Now we'll create a mask. Initially, this mask will be nothing but a 0 image, which we can use NumPy to create for us. Zeros like image. And this will create a mask, an empty image. And this mask will be now filled with just this triangle region that we are interested in. So we'll call this triangle. Okay, triangle. And this triangle is going to be a shape that we will define based on the coordinates of these points in the image. So this triangle is going to be defined by 3 points. And we'll start defining these points. We'll create an array. And we'll create an array basically defining where are all these locations. We'll have another array in between. And this will be the first triangle point, which will be here. And we will call it as maybe height, as big as the height of the image. So we will call, okay, 0. It should start from 0. And it should be as big as the height of the image. So this is the height of the image. And it's somewhere here. So 0, x-axis is, of course, 0. And the y-axis is almost the height of the image. So we'll say the first coordinate is located here, which will be nothing but 0, comma, height. Good. So once we have the first coordinate pointed out, we can then find out the midpoint of the coordinate. And for this purpose, it's better to know what the size of the image is, what the shape of the image is. And for that purpose, what we can do is once we have this Canny image or the screenshot image, we can just simply print the shape of the image. So we'll say frame dot print. And I'll comment all this portion so we are not going through all the Canny part at this moment. So frame dot shape. That'll give us the width and the height of the image. We'll just simply run this. And it's giving us the width and the height as 534 and 935. So the height is 534 and the height, the width is 935. So we'll use that. Okay, so the height is approximately 534, which will be used here. The next is this midpoint of the triangle. So we'll have the midpoint somewhere here. That way we can take note of every action here. So we'll call it something like the height is approximately maybe half of the image, and the width is somewhere also almost the half of the image. But we'll give that a try and see how that works. So the height is about the point here is going to be about 935 by 2. The x coordinate would be somewhere between 935 by 2. And we can call it as width divided by 2. And similarly, height divided by 2. So we're just specifying where the approximate triangle point is. So this is the first point, this is the second point, and now the third point. The third point looks like it's a little bit next to the height, next to the edge of the image. We'll call it another point, and we'll say if this time the width is width, the x-axis is nothing but the width of the image, and the height is a little bit less than the edge. We can say height minus 10 maybe. So height is minus 10, and let's see how this comes out to be. But once we have all these functions defined, we define the coordinate, and we'll just create a numpy array of int 32. We're telling this array or this mask is nothing but an integer variable, and you want to fill this information with these coordinates. So this is just going to be the shape of that triangle. Once we have this triangle filled, we'll now, the original mask image that we had, it was a zeros image, right? We will use this triangle portion and fill the mask with a white color, so we can then use it to subtract from the original image. So we'll call the mask function. There's a function called cv2 fill poly. What this does is, based on the shape that you give, like in our case, it's going to be a triangle. Based on the shape, it will fill the mask with the color that you want. So fill poly mask. So we want to fill the mask image with the triangle information across the triangle that we created with a 255 color. So it's going to be filled with 255, nothing but white color. So it will now create a mask which is nothing but 255. And once we have this information done, we will create, we'll simply mask or subtract the mask from the original image. And for that purpose, we'll create a mask image using the mask, and we'll call a bitwise AND operation. So CV bitwise and IMG mask. So what this is doing is it's creating a bitwise AND operation between the original image, the Canny original image, and the mask image. The mask image is nothing but the triangle, right? So it will create a bitwise AND. Wherever the mask is located, it should give out that portion and reject everything else. So all this noise will be simply removed. And we'll just return the masked image for our purpose. Now let's come back here. We don't need the frame shape anymore. We have the Canny image. Let me uncomment this as well. So once we have the Canny image, we send it to the region of interest, right? So we'll call it as M for a mask. M image is equal to region of interest, Canny. So Canny image. We give the Canny image. And we'll now display the M underscore IMG, so we can see how this region of interest came out to be. Running this, there seems to be a code error issue with the function, and this is going to be on, let me minimize this and see what's happening here. Oh, we did not create an array here. So it's going to be an array. So the triangle should be an array. And this array will now create based on the points that we're giving. Run this. Oh, yep. So it looks like it is able to create this, but it seems like most of the lanes that we are also interested in are also gone. So either this particular portion is a little bit smaller here. So it seems like the midpoint is somewhere here. We need to extend this to somewhere here. It can take the portion of all the lanes. In fact, this lane is right here. So let's come back here, and instead of the height being height by 2, we will give it height by 2 minus 100. Let's see how that comes out. So it's now able to take this information, but it's missing some portion of the lane from this angle. So we'll try to, and it's also taking a little bit of extra information from this portion, which we are not interested in. So instead of minus 100, we can maybe try 70 and see if that works out. So it's removed a little bit of that portion, but this thing has to improve. We come back here, and instead of height being 10, we can try giving 50 and see how that works out. Okay, so I think that's fairly good. It's able to take the lanes from this side, and it's also able to take the lanes from this side. That seems good. Maybe if I do a little bit more, 60, and see if it can take anything else. I think that's good enough for us before we start breaking the system. So this is good enough for us. So we can have now we have information about the lanes, these lanes, and we don't have the extra noise. There are certain lanes, or there are certain edges, like the car here, and these noise that is present here, which is of no interest for us. but for that, we have other functions that can remove that noise. We have taken care of the major portion for OpenCV, and OpenCV has some other function that it can take care of itself. So let's comment this portion once again. And once we have the region of interest, we will use something called as Hough lines or Hough line transform. This Hough line transform can basically take certain images, the edges of the image, and it can give out an approximate line based on those edges. And for that purpose, there is a function called Hough lines transform. We'll just make a function Hough lines, which will take the image that we provide from the region of interest, and it will create some Hough lines for us. So this function is nothing but going to take this edge image that we saw and create a line from that edge. So once we have the edges, now we want to break it down into lines so that OpenCV can then draw those lines for us. So CV2 Hough lines P. And this is going to be a function which will take certain parameters and open this. I'll maximize this so we can easily see all those parameters. So we have the image that we need. We have number 2 here. We have number pi by 180. These are nothing but filter values that are needed by the Hough line transform. And whenever we see the lines are not being drawn properly, we come back to this function and just tweak the parameters that we are giving here. This is going to be an array that we're going to specify. And the minimum length, line length, is going to be, let's say, 40 in our case. But this is just an approximation of how big the lines are. So we saw how those edges from the car and all those noise that was left over, it created those edges. And this minimum line function, which is 40, it'll take care of that and it'll remove all those edges that are of no use to us. And the lanes that we are interested in, those are big lanes, which is going to be 40. And this is specifying where the information is going to be coming from. The maximum gap, maximum line gap. So in our case, the maximum line gap will give it as 10 maybe, because the left lane is towards the end, the right lane is towards the extreme right. We can easily give 50, but just to be on the safe side, we'll give 10 and see how that works. We can always come back and fix it if there's an issue. So once we have CV Hough lines transform, we can just simply return this image. We'll say return Hough line that we created. Now it seems like OpenCV did not like the way we created this function, because this should be a capital H, Hough lines P. So that should hopefully take care of it, but it still does not like certain things that we have done. I think the bracket, this particular bracket shouldn't have closed over at this stage. I think that is now good. Okay, so we have the return, which is nothing but the Hough lines that we have called from the function. Now, once we have the Hough lines created, let's uncomment all of this. And we can now return the lines, right? The Hough lines, the H line. And this is going to be the function Hough lines, which will take the masked image for us. So now these lines are nothing but coordinates, so we can't actually display them. So we'll just print each line and see what all lines it has detected for us. But once we have this, I don't think we need to display this, so we'll just simply come back and see how this works. So let's run this, and it is creating a couple of lines. You can see one image created so many lines, and that's because if we see the image, uncomment this. If we see this image, you can still see that the lanes have 1 or 2 lines. In this case, it has 1 or 4 lines. So all this is, in fact, noise. From our human eye, we see them as one lane, or one particular definition of a lane. But these lines are so many that the computer sees it as multiple lines, and it will get confused between which line to follow and which one to not to use. So for that purpose, we will average all these multiple lines into one or two lines that we actually need. So let me comment this back again. So we don't need the IMShow function. And once we have the Hough lines, we will now create an average of the function. So once the Hough lines are created, we'll create an average of all those lines. So all the lines on the left-hand side will be averaged into one, and all the lines on the right-hand side will be on the right. And for that, this is going to be a little bit on the complicated side. Stay with me. And if you find something difficult, leave a comment, and I'll come back and try to help you. So we'll create an average slope intercept. So we'll say create average, and this is nothing but it's all dividing. It will divide all these lines based on the slope. So all the slopes which define the lines on the left hand side will be 1, and all the slopes of the other side, which is on the right hand side, it will be all under 1. So you're just using that slope format to basically average all the external lines that we see. So intercept, and it can use the image that we give, and it will also take the lines that came out of Hough lines. So this function is now going to take the image and create a Hough lines on top of that. We'll just give some space here. Now the first thing is we'll create an array that can take in all the lines from the left hand side. We'll call it as an array, so it can store information about all the left lines. We'll also create a right fit, which is going to take all the information of the right slopes. It will now go through each line from the lines function that we have. So we can call for line in lines, and each line is defined by 2 points, and each point has an x coordinate and a y coordinate. So we say for x1, y1, x2, y2. We have x1 and y1, x2 and y2 in line, and we'll now create a fit function that can take this information and create a line, and from that line it can create a slope and an intercept for us. The function of a line is given by y is equal to mx plus c. So it's going to create that thing for us. So the slope is, the intercept is c, and the m is the slope. So it's going to take that information, and it'll create a function called fit np polyfit. And this function can take 2 coordinates and give out the parameters or the properties of the coordinate, of the Cartesian coordinate. So x1, x2, bracket y1, y2, 1. So this is the type of coordinate or Cartesian that we are playing with. The slope is equal to the fit comma 0. So this fit will have information about the line. It will have the slope, and it will have information about the intercept. The slope is fit 0, and the intercept is equal to fit 1. The fit takes information from the slope and the intercept. And now we can simply use a parameter to say, okay, if the slope is on the left-hand side, if the slope is negative, because the left line is slanted on the right-hand side, whereas the lanes on the right-hand side are slanted on the left-hand side. So we can just simply say this: if the slope is less than 0, it's the it's the lane on the left-hand side. Similarly, if the slope is greater than 0, it's a slope on the right-hand side. So we just create this slope function, and if the slope is less than 0, we say that left fit dot append, and we are just giving information about the line slope slash intercept, and else it's going to be a right fit append slope intercept. I'm just taking the information about the information, the line flip. Once we have all of this, we can now create, using all the left fit lines, all the lines from the left hand side and all the lines on the right hand side, we can create an average of those lines. So we can come back here and we say lift with average. So this is the average of all the left hand side lines. We say average of all the left fit. So all the left lines come in one place and give us an average. Good. Similarly, all the right fit average, let's create an average of all of them. Right fit axis is equal to 0. Okay. So all of them are created. So this is just the left average line and this is the right average line. And from this, now we will create back the points that we need for the image. So because OpenCV draws it based on points, so we will now need the x1, y1, y1, or x2, y2. So the left line of all the average is equal to, we'll call a function. We'll call another function which can create points, and we'll define it here. And it can take information and then create all the points from the slope and the intercept. Because normally we can get the slope and the intercept, and using that we can just create all the lines. So let's come back here and we'll take definition, make points, and this function can take the slope and the intercept and draw the coordinate or find the coordinate on the image that we have, and the lines given by slope and intercept. So this lines or line SI, it can convert from slope and intercept to a point, because here what we did was, in order to differentiate between the slopes, we converted the x1, y1, x2, y2 into a slope and an intercept format. So all these lines are in the slope and intercept format, and that's not going to work for us, because in order for us to draw these lines, we do need the x1, y1, and y1 and y2 coordinates. So these are back. So we're converting this slope intercept format back to its x1, y1, and x2, y2 format. And for that, it'll take the slope and the intercept, and it'll create, so the slope and intercept, which is given by the lines I, it'll create and it'll also take the height of the image. Height is equal to img.shape 0, and it will create now let's find the coordinates, the y1, y2 coordinate. And for that purpose, we have this function, right? Y is equal to mx plus c. So x is equal to nothing but y minus c divided by this m. So y is equal to mx plus c. So we will use this formula to go back and find our x and y coordinates. And for that purpose, we will now first use the x1 is equal to integer, and we will now call the y1 minus intercept, which is y minus c, and this whole divided by the slope. So the slope is found. Then you have x2, which is equal to int, and you have another function y2 minus intercept slope. But before we do this particular portion, we do need to find y1 and y2. So we know that y1 is equal to somewhere at the height of the portion. So y1 is one of the regions towards the end of the lane. So we say, because you remember we had this function where the height is approximately where the portion is located. So height, and we have height minus 60. So somewhere towards the end is where we have all the lanes converging. We can simply say y is nothing but maybe the height, and y2 is somewhere integer, a little bit less than the height. So we can say y1 multiplied by maybe a little bit less. So I would say half of the height could be. So half of the height will give it as half of the height, or maybe 3/4 of the height. We can say multiplied by 3.0 divided by 4. So 3/4 of the height. So we have this image, right? So we are saying that the y is somewhere here, y1 is somewhere here, y2 is somewhere here. So we're just specifying an approximate portion of where this y, or the region of the height, is located. Similarly, in this case, we will have some issue because here we're assuming that the y is towards the end, but it's actually a little bit over the edge. So we'll see the arrow, we'll see the lane drawn a little bit towards the side, but that's okay. It's not going to cause so much of harm. We can always tweak it here and differentiate based on the slope. But for our purpose, in this case, it should be okay for us. Once we have return all these points that we have. So we have x1, y1, we have x2, y2. So all of these x2, y2 are nothing but lines. So it's creating that make points for us. So the left line is going to be based on the make points using the image that we have, make points img left fit average. Once we have this, we call right line equal to, again, the right line is going to be make points img right fit average. So we'll call it as average equal to lines, left line and right line. So we have left line and right line, and we can just return these average lines. We'll call it as average line. So just it's basically returning all these lines that we already have, and now using these lines we can then draw the function. So if we call this function back again, so using the Hough lines, we send this Hough line to AVG lines, and it gives us average lines. We have this average slope intercept, right? We can call this average slope intercept, and we can give, okay, the average slope intercept is nothing but the frame or the M image that we had, or maybe the frame itself, doesn't matter. We have frame, comma, lines, the H lines, and once we have this H lines given, it should be able to go through all of them and give out the average lines for us. We'll now print AVG lines. So hopefully it should not print as many lines as we saw with the Hough line. So run this, see how that works. So we can see that it's giving us two lines, two forms of lines here, and the other one is right here. So it's able to go through all the image and give us the information. This does not look good. The amount of information here is 100,637. Where is it getting these big numbers from? It's something to do with the frame size that we are giving here. So we have the IMG. So this IMG is going up here and it's coming out from here. And we are giving the shape of the size. Print this shape and see what the height of this shape is. Or maybe this particular height is too big for it. Understand? Even we'll look into it and see where we are on. We have 534 by 534 for each of them, which is okay. So that's not the issue. Is it this particular height? No, I think it's this one, which is calling that print y2. because those numbers don't look good. Oh, this is 400. So it's got to be those x1s and x2s. X1s and x2s. What is the mistake here? Print x1 and see what's coming up. Yep, that's where you're getting that issue of 736 and 1249. These extreme edges. That's coming because the intercept is too big. That's why you're getting those big numbers. And we have the slope, which is fine. If you just simply print the intercept, comma, slope, let's see that comes. You have the slope and the intercept. Yeah, you can see the slope is already 448 and the slope is minus and positive, which is one for the left line and one for the right line, which is good. Okay, well, let's run this. Let's see how this comes out to be. This is what happens when you're easiest way to just debug and see where the issue comes out to be. Okay, once we have the average lines, we can now simply draw these lines and see how the function comes out to be. We can see how they're where the lines are getting messed up. We'll call this function display lines average. Okay, so all the average lines that we have, let's display them. Okay, so we call this line. Our line image, it's going to be a new image, and we'll draw everything on this image. So 0 like, so it'll take the height and the width from the img and create a zeros like image called line image. So once we have this created, it will now call if line is not none, go ahead and draw. For line in line, for x1, y1, x2, y2, in line, pv2 line img, 1, y1. So it's defined by two coordinates, right? X2, y2, 0, 0, 255, 10, and it should return the image, the final image. So when, once we have all of this defined, we can just call a function called, once we have the print lines, we can say in line image, lines image is equal to display lines average on the frame using the average lines that we have here. So we'll uncomment this, we'll uncomment this, we'll uncomment this. Instead of using M image, we'll give lines image and minimize this and run this. So it's creating these two lines right here, but there is some issue here. The edges are not in the right places. The height of the line is also not good, but this is something which we can rectify by just changing those parameters that we found out there. So the H value here should be a little bit different. The H value that we give, H is good. So instead of 3 by 4, we should probably give y is equal to e by maybe 5, and or reduce the amount with regards to, so maybe 0.8 version of the height. So, or maybe less than half of the height. Let's give that way and see how that works out. So y1 is equal to half of this, so 1.0. Oh, we did not close this. Now let's run this. And we can see now this is going to be a little bit on the edge, which we are also not interested in. We come back and instead of 1 by 2, we give, okay, by 3.0 by 5. Let's see if that works out for us. Yeah, so it's giving out some region. Now we need to close that gap with regards to slope. So we can fix that by looking into where the lines are starting from. Okay. For now, I think we have a very lengthy video that's going on. The next step, we will see how we can control the car and use this lane information to guide whether it has to turn right and left. Yep. So we'll meet you in the next video.